Hello, everyone. Welcome to video 5. So what I thought I would do in this video is I'm going to still be using those PDF notes, like the notes, the lecture notes, but I'm going to write on the yellow pad because it gives some more room, and then I can kind of make some comments more easily. And also, more practically, this app with the yellow pad app, Notability, it doesn't freeze nearly as much as the one with the PDF. And I think the pencil functions are a bit better. Maybe we can see how this works. If you like the other way better, I can go back to it. But I thought we would try this for a bit, and it's not too much more work for me to write out the questions and that are on the PDF. So in this case, so in this lecture, we're going to talk about two new differentiation rules, which are far less, how I say, intuitive and easy to implement than the ones we've done so far, than the power rule, sum rule, and this constant multiple rule. But they allow us to do a lot more. So there's a price to be paid, but we'll be able to solve a lot more problems. So the first rule I want to talk about today is the product rule, which is a rule that allows us to differentiate a product of functions. So what I'm saying is the following. So suppose we have a function h at x, which is f at x times g at x, right? And we would like to compute, we seek to compute the derivative h prime at x in terms of the derivatives of f and g Okay, so like I was saying on the other live meeting, that once we get beyond the initial derivative rules, the other derivative rules like the product rule and in a moment we'll do the quotient rule, these are far less intuitive than the sum rule and the constant multiple rule. So here's what the rule is. It's not what you would kind of hope for it to be. You might hope that the derivative of derivative of h is just the product of the derivatives of f and g. That is not true. It's a more complicated formula, and it's basically because of this formula the derivative in some sense really works the way it does. But that's a different story. Okay, so what it is the derivative of h at x is the derivative of the f, but not times the derivative of g, times g itself. Then there's another term. Then you take f times the derivative of g. So in words, the derivative of the product of f and g is the derivative of f times derivative of g. I'll just write deriv for derivative. Plus derivative of g times f. And again, I kind of say this rule in my head over and over again to help understand this rule and, derivative of g, not derivative of g prime. To help understand this rule and to like internalize it when I'm performing the computations when I'm performing the examples. Okay, so an important thing to note, so just, notice this is quite important. The derivative of the product is not equal to the product of the derivatives. So that's the most common mistake. And that's kind of what you would want it to be, but that's just not true. And unlike in the case of the sum rule and the constant multiple rule, where I was able to kind of give you a explanation in some sense as to why geometrically this is like, those rules work the way they do in terms of slopes and things like that, it's much harder to understand this rule geometrically. And to be honest, I don't have a good geometric understanding of this rule. It's something you have to really prove using algebra. It's really an algebraic property. So at least at this stage. So anyways, because this rule is a little more complicated than the previous ones. It takes some getting used to. We'll do a few examples here. I'll be happy to do more from the homework, more in the live meeting when we get together. Okay, so next page, here. Oops. Examples of the product rule. The first example is quite basic. So from the PDF, find the derivative of function y is equal to minus x squared plus 2 over times x over 2 minus 1. Okay. So to find the derivative, this is a product of two functions. Now you could, if the product rule isn't completely necessary here. In the next example, it's much more necessary. But because you could expand this out, you could FOIL this out, and then you'd have a polynomial and you could use the power rule and sum rule, like in the previous questions. But for this one, really you have to, it's more convenient to use the product rule here, and we should practice with it. So I'll think of this as my F, and this is my G in the description above. There it is. Okay. And we'll apply the product rule. So applying the product rule, we have that y prime is the derivative of f of x times g plus f times the derivative of g. Or g times the derivative of f. You can write it either way. I can write the x here. Okay, now each of these, right, the derivative of f, the derivative of g, we can obtain these using the techniques of the previous section. So I'm not going to go through the whole sum rule thing again, product rule, sum rule with power rule thing. We've done that several times now, and you kind of should be familiar enough with it, comfortable enough with that you can do that fairly easily without having to go all the way back to basics in some sense. So you don't have to write out the sum of the derivatives, you just do that in your head. So this is minus 2x, derivative of f is minus 2x, the derivative of 2 is 0, times this guy. And then plus the f. Derivative of g is just 1/2. And that's the derivative. We could expand this out if we want. I don't think there's a tremendous amount of point to that, but I can do that if you like. So just practice the algebra. So it's minus x squared plus 2x minus x squared over 2 plus 1. And so we get y prime is minus 3/2 x squared plus 2x plus 1. Okay, so I just noticed, sorry, in the notes that this was an x cubed instead of an x squared. Not a big deal. You could use the same method. We'll stick with this example for now. And if we want to do the x cubed example in class, we can. Okay, example 2. Okay, so find the instantaneous rate of change. I'll put that in parentheses. When x is 1 for the function f at x is equal to x cubed minus 5x squared plus 2x minus 7 times 2x to the 4th minus 10x cubed plus 15x plus 9. So now I'm making sure I'm copying it correctly this time. Okay, so let's make sure that's right. That's good. Okay, so now this one, I mean, you really want to use the product rule here. You don't want to be expanding this out. This is each factor has 4 terms. It's a very complicated expansion. So we really want to be using the product rule. We have to use slightly different notation here because this is called f. So I'll think of this first function as g. Think of this first function as h. In the formula for the rule, it doesn't matter what they're called, right? What it says, the rule now says that f prime at x is the derivative of the first factor times the second plus the second factor, plus the derivative of the second factor times the first. Okay, so it doesn't matter what's called f and g or h in this, right? This is whatever functions are involved in the product. That's what you need to know. Okay, so again, this is applying the product rule with what we did in the previous section, derivatives of powers of x, sums and multiples of powers of x, which hopefully you're very comfortable with now. So I can focus on the product rule. So applying the product rule, and I'll write it this way, slightly different notation. We have f prime at x is the derivative of the first factor times the second factor, unfortunately running out of room, plus the derivative of the second factor times the first factor. And that's okay. So now that's the product rule, and now we have to compute the individual derivatives. So if you like this kind of notation here, right, then this is your derivative of g, this guy here. This is your h, and this is your derivative of h, and this is your g. And that in that notation. But again, what the product rule is doing is it's saying you have product 2 functions, derivative first times the second plus derivative second times the first. Okay, so let's do this. Okay, so now applying the power rule with sum rule, all that jazz. Okay, the derivative of g is 3x squared minus 10x plus 2. Let me just multiply that by this guy. And then we add this next term here, right? So we get, again, derivative of h by power rule is 8x cubed minus 30x squared plus 15, and then you multiply by the next guy. Okay, so this looks pretty ugly, and you don't want to expand this out very much. But remember what we were after. We were after wasn't the formula for the derivative. So we want to find the instantaneous rate of change when the function, for this function when x equals 1. Instantaneous rate of change, that's the slope at 1, or that's the derivative of 1. So the instantaneous rate of change when the function is evaluated at 1 is f prime at 1. So to find this, we just need to evaluate this whole mess, right? We need to evaluate this mess at 1. So we just need to evaluate the above formula for f at x equals 1. Okay, so this is a bit tedious, but you can use a calculator. So let's do the first step. So f prime at 1 is 3 minus 10 plus 2 times 2 minus 10 plus 15 plus 9, and then plus 8 minus 30, just plugging in 1 everywhere for x, plus 15, 1 minus 5, plus 2 minus 7. And then you would just, you have to go and, write this out, and you would find, you would get some answer in the end. So, so now let me write this out with a calculator so you can compute on calculator if you'd like, or you can compute by hand if you're really looking for something to do, but I don't know if I'd recommend that. Okay, so these are the kind of things that we can do with product rules. You see, it's kind of a more lengthy computation. It's more tedious. And you need to be really comfortable to be able to do these kind of computations. You need to be really comfortable with the previous derivative rules. They need to kind of be at your fingertips because they come out as parts of a much more involved computation. Sorry, steps in a much more involved computation. And it only kind of gets worse from here. So the next rule is the quotient rule, which is even more tedious. Okay, so I'm going to be honest with you guys. This is my least favorite rule in calculus, and it's the most difficult one to maintain, to implement and simplify. It can be obtained, maybe in the class I'll talk about how you can kind of obtain it from the product rule, but it's kind of an elaboration of the product rule and some other techniques that we'll learn in a bit, but very, very tedious. Okay, so this is when this is the rule for differentiating a quotient of functions f of x over g at x. Like, for example, some function like h at x is equal to x squared plus 1 over x minus 1. Some function like that. Okay, where you can't simplify it algebraically. Like x squared plus 1 doesn't factor, so you can't cancel things. Okay, so how do you handle this? So the formula is the following. So the derivative of the quotient is the derivative of the numerator, or the top, times the bottom, minus, that's really key, minus the derivative of the bottom times the top all over the bottom squared. Okay, so kind of in like words, or like short, so h prime at x is deriv top times bottom minus derivative bottom times top all over bottom squared. As you imagine, this could be kind of a mess to implement at times. So we'll do some examples, and I'm more than happy to do more examples in the live session or you know, we can find time to talk about more about it. Okay, so examples. Find the derivative of the function y equals x squared plus 1 all over x squared plus x plus 7. That's the guy. Okay. So again, our top, if you want to think about those in this notation we did above, you can think about it as f and a g. Again, it doesn't matter what you call them. So you can think of this as your f, this is your g, but this is kind of like top versus bottom, numerator versus denominator. Okay, so using the quotient rule, we get the derivative of y, again, so the derivative of the top times the bottom minus the derivative of the bottom times the top, so that's a 1, all over the square of the bottom. Okay, so that's the first step. That's actually using the quotient rule. And now the next thing is we have to find the derivatives that are involved in the numerator. And that's using the material from the previous week, right? This power rule combined with some rule type stuff. So we do this, we get, y prime is derivative of x squared plus 1 is 2x. So it's 2x times x squared plus x plus 7 minus, okay, derivative of x squared plus x plus 7 is 2x plus 1, right? Derivative of x squared is 2x, derivative of x is 1, 7 is 0, times x squared plus 1, all over x squared plus x plus 7, all squared. Whew. Okay, now it's good form to simplify the numerator if it's not too ugly. It's kind of good practice, especially in applications. It can help to have the numerator simplified down as much as you can possibly get it to. So let's try to simplify the numerator. So when we do that, what are we going to get? So we get 2x times x squared. So that's 2x cubed. 2x times x is 2x squared. And then you get 2x times 7 is 14x. Then you go to the other one. Okay, so 2x times 2x, and make sure you have your parenthesis here, right? This whole thing is being subtracted. So here's a common mistake. So the whole thing is being subtracted. Make sure that when you do the simplification, you have parentheses around everything, so you'll subtract all these terms. Okay, that's a common error. So 2x times x squared is 2x cubed, which is good because that will subtract. And you get plus 2x plus x squared plus 1, and that's all subtracted, right? You need the parentheses around everything. Okay, and then and the denominator will have the usual jazz. So we'll have x squared plus x plus 7, and there's no point expanding the denominator. Okay. If anything happens, it's that somehow there's a common factor you can cancel with the denominator. If you expand a factor denominator, you won't see that. So leave it as is. So, okay, we can do some cancellation. This guy cancels here. The 2x squared term, we'll subtract an x squared, get an x squared, so we'll get x, we'll get x squared. And then see the 14x, we subtract 2x, we get 12x, and then we just subtract 1. And this is all over that guy, x squared plus x plus 7 squared. And that's as simple as it's going to get. Okay, so these take a little while to get used to. And for me, I think it was always tricky to remember the exact form of the quotient rule. So I can always remember that it's the square of the denominator that shows up. But because there's a negative here in the rule, it matters which term comes first, right? And with the product rule, if you go back and look at the product rule, right, you just have a plus. Like, where did it go at the beginning here? So in the product rule, right, there's a plus. So I was always doing derivative of the first guy, derivative of the f, derivative of the first factor times the second plus, derivative of second factor times the first. But it didn't matter like which order you did that in, because addition, like, it doesn't matter which way you add things, right? A plus b is b plus a. But for the quotient rule, it does matter, right? Which one gets the negative sign. So it's the terms involving the derivative of the bottom function that gets the negative. So before I do the next example, let me which is a bit more involved. Let me do some, just make some notes or remarks about common mistakes that are made with the quotient rule. And so the first one is kind of the one I was talking about. So having the wrong, having the negative sign with the wrong term in the numerator. So in front of minus f prime x gx instead of g at x, g prime at x, f at x. So that's the most common mistake. So again, so this is for h at x equals f at x over g at x. Very common mistake. The other thing is actually having a plus sign in the numerator instead of a negative sign. So, which is even worse. Having a plus sign in the numerator rather than a negative sign. So that means, what do I mean by that? Psi. Yeah, I do psi when I see that. I.e., using the incorrect formula. That h prime at x is f prime at x times g at x plus g prime at x times f at x. I mean, I've seen this enough that it happens. I've seen this enough times that I do want to warn you. And this is just like completely wrong. Okay, so you do have a negative sign. That's really what makes it substantially more complicated. And the third, so these are kind of an increasing order of severity. The third mistake, which I really hope you guys don't make, is one it's like involving algebra. So algebra mistakes with quotients. In particular, on incorrect simplification. So these are things like 1 over a plus b equals 1 over a plus 1 over b, that kind of garbage. And to some extent, along the same lines, something like this equals 1 over x plus 1. Okay, so breaking up denominators, right? When you cannot, essentially. So remember, to add fractions, you need a common denominator. So 1 over a plus b does not split up into 1 over a plus 1 over b. And something like this does not split up into x over x squared plus 1, which is that. Okay, so these are like fatal mistakes that just kill people all the time. So these are like things you really want to avoid with the quotient rule. So your algebra needs to be you need to be pretty comfortable. Okay, so enough with that. So let's do the last example. Okay, so and this is a little more involved, but we can handle it. So for what values does the function f at x equals x plus 4 over 6 minus x have a slope of 5? So make sure this looks like a 6 here. There, that's better. Have a slope of 5. Okay, so we need to translate this question about geometry, it's a kind of geometric question, into a calculus question. Question about computing derivatives where we can apply the quotient rule. So first, translate this question into a question about computing derivatives, into a calculus question, let's put it that way, into a calculus question. Okay, slope of 5. What is the slope? Slope is given by the derivative, right? So we want to figure out the points on for what values, so I should say, so for what x values, do we have a slope of 5? So the slope at x is the derivative of x at x, right? The derivative is the slope machine. You put in the x, it tells you the slope of the tangent line at x. So what we're being told to find is for which values of x does the derivative equal 5? So in other words, we want to find the values of x for which the derivative is equal to 5. i.e., we want to solve the equation f prime at x equals 5 for x. Okay, but to do this, so that's now we've translated this kind of geometric question into an equation or a problem that we should be able to solve, knowing the techniques that we know at this point. And that's what a lot of math is. Translating something you want to find into a problem you know how to solve. And that's not always easy. Okay, so to solve this equation, right, we clearly at first have to find the derivative of f. And that's where the quotient rule comes in. So clearly we need to find f prime at x. Oops. And this is where the quotient rule will come in. Okay, so f prime at x from the quotient rule. So where did f at x go? It's kind of way up in space, right? So maybe I should write it again. So f at x is x plus 4 over x minus 6. So I'm gonna, oh, sorry, 6 minus x. Okay, I'm gonna write the x plus 4 plus x is x plus 4. So by the quotient rule, f prime at x is the derivative of the top times the bottom minus the derivative of the bottom times the top all over the square of the bottom. Okay, so that's applying the quotient rule. But now we've got to we've got to find these derivatives, which luckily are fairly easy. So the derivative of x plus 4 is just 1, because derivative of x is 1, derivative of 4 is 0. So I don't even need to write a 1 there. I can just, so you just have here 6 minus x. And subtract, okay, the derivative of 6 minus x is minus 1. And then I have x plus 4. And this is all over. Oh, let me clean that up. This is all over the square of the denominator, 6 minus x. And so f prime of x is 6 minus x. Now minus is plus, right? So it's plus x plus 4. All over, sorry, clean up, 6 minus x squared. And now this simplifies nicely. So f prime of x is actually 10 all over 6 minus x squared. And that's the derivative, right? That's the derivative we wanted. So just put it in the box, give this equation a name, call it star. Now we want to use that formula star that we just found in this equation, f prime at x equals 5, to solve for x. So now we substitute this expression for f prime at x into the equation. F prime at x equals 5 and solve for x. So you do that, you get, now this requires, now the calculus is done, and so now we're just doing algebra. So this requires doing this 10 over 6 minus x squared equals, clean that up a bit, equals 5. So you multiply both sides by 6 minus x squared, you get the equation 10 is 5 times 6 minus x all squared. And now you have to FOIL this out and get a quadratic equation that you can solve for x using the quadratic formula. So this is 536 minus 2 times x plus x squared. And then you can do a little bit cancellation here, right? Because the 5 can be divided out both sides of the equation, divide by 5, divide by 5. That'll make the algebra a little nicer. So you get 2 equals 36 minus 2x plus x squared. And then we can get the equation that x squared minus 2x plus 34 equals 0. Okay, so this is something that doesn't factor, obviously. It has actually irrational roots. So I will let you fill in the details, but using the quadratic equation, you get the solutions x equals 6 plus or minus root 2. So we talked about the quadratic equation in one of our review lectures. Hopefully you can handle that on your own. If you're having trouble, let me know. The numbers work out okay, not fantastically, but they're basically fine. But I won't go through all the algebra there. So this is more of a complicated problem, right? You want to find out like where you have slope 5. So that means where's the derivative equal to 5? So you have to find the derivative using the quotient rule, then set it equal to 5, like we did here, right? Sorry, that's good. Check. And solve for x. And you get a quadratic equation involving x. And if you use a quadratic formula, so using the quadratic formula, you get the solutions quite easily. Okay, so just maybe I should write a conclusion. So the conclusion is that the function f of x equals 4 plus x over 6 minus s has slope equal to 5. Exactly at the x values. Six plus or minus √2. Okay, so this is going to be like, these questions are going to be much trickier than the previous ones. So try to get started on the homework ASAP, and I'll be more than happy to help you with these problems. And so will Charles, your pal. And so after this, we have to start. Okay, so the next step is to do derivatives of compositions of functions, and this is even trickier, I think, in some way to get down. And after that, we have done a lot of the hard rules, and then it's about learning new functions and applying the rules to some new functions. All right, thanks for tuning in, and I'll see you in the live meeting.